Hi, and welcome to this recording for Unit 68. Unit 68 basically addresses the neutron stars. This is one of the stages or the final stages of a massive star. I mean, if it's not that massive, honestly, because there is another ending also for massive stars, and that is black holes. That fate is usually reserved for even more massive stars. Anyway, neutron stars are actually an interesting topic because they have classifications on their own, and also they may even have phases of their own. So it's not really a one end state. Okay. So basically, we're going to see how they were discovered, and they were confused actually with something else. And then, at least the pulsars, the version that emits extreme high radiation, especially in the radio wave region, and then explain how neutron stars basically spin, and that how that became an explanation. And there is a correlation between actually a remnants of a supernova and sources of these pulsars. So that's why we know that they're actually neutron stars. And then describe how milliseconds and high energy pulsars arise. Explain what we know about the internal structure of a neutron star. A lot of these things, honestly, are speculations. Not really speculation, I should say, models based on theoretical models, numerical simulations, and also measurements related to, for example, emission of this electromagnetic radiation. And also describe how neutron stars merge. And at least in the unit in here, we're going to talk about it as being something that is potential, but now we know it's actually in light of the current, basically, observations based on the LIGO and also the different observatories, that there are actually in cases where neutron stars and neutron stars collide. And this could explain, not only could explain, but actually the base of which most of the supermassive, or at least the heavier elements in the periodic table are formed. It's through this process, actually. Okay, so let's get into it. So pulsars are extremely fast pulsating stars. These are waves, or at least emissions, that are extreme high frequency. I'm looking here at a range of 1 second. See how many pulses I'm looking at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's almost every tenth of a second, or less than a tenth of a second, there is a pulsation. Okay? So that's the period. Okay? So it's 0.9 seconds. So it's extremely fast moving object. You cannot believe how fast that object is, especially considering that it was that this size of the object, at least in terms of mass, was the same size of a star, basically, like the sun. So initially, when they were discovered, of course, they were believed initially that they are some sort of a signal, because this is a radio wave after all, from some sort of aliens, but it turns out to have a better explanation related to this models in here, related to how stars are. Some of the pulsars are actually pulsating a lot slower, and here it's probably 1 pulse per second, okay, or roughly 1.5 pulse per, because I'm looking at 3 pulses in 2 seconds, so it's basically 1.5 pulse per second. That's basically the rate. So some of them are extremely faster than others. That's really the idea behind it. So imagine I have a supermassive object, okay? Big object. Tremendous magnetic field being produced by it because of the fact that these are neutron stars after all, and neutron stars are made up mainly of neutrons, and each neutron has its own magnetic field. So a star of that stuff. So there is tremendous magnetic field, and the fact that it's spinning super fast, and if the axis of rotation and the magnetic field make an angle with one another, then that would produce this asymmetry will produce a lot of basically particles that are going to be affected by that rotating magnetic field. Okay, so they are going to be ejected, and those materials, they are going to be injected in both directions against the poles of rotations. And if we happen to be in the path of those, that's when we detect the signal. because it's pulsating, because it's rotating super fast, then the next time it's going to go through again, it's going to send it. Similar to a lighthouse basically spinning around to just indicate the ships in the ocean where the shore is. So that's basically what they are. And they're extremely highly regular, so that you know, so that these are predictable when you're going to see them. So if it's uh, rotating, you can actually detect this and you can predict it when it's going to happen. So a lot of them, and they actually can be used as clocks if you wish, because they're so accurate in their rotation and repetitive. Again, this is the Crab Nebula. In here, if you go from roughly slightly more than 0.2 seconds all the way to 0.8 seconds, you're looking for about slightly more than half a second in terms of pulsations in here. So where is the source of that? The sun takes a few weeks to go spin, and the stars in general, a few weeks to spin around their own axis. The sun is not going to produce a pulsar, a neutron star, by the way. So think about something even more massive than the sun. And after it turns out to its fuel, and after it sheds all of its materials and goes supernova. So it's going to shrink for the most part. At least the core is going to shrink, okay? Where the electrons are going to be pressed against the protons and convert them into neutrons. We talked about that in one of the previous units. So now that central object, which is more than the size of the sun, or about the size of the sun at least, and it's shrinking. So in this case, there is something called the angular momentum, and we talked about that one also in some previous units. The angular momentum is conserved because there is no external agent that is doing that. So it's all internal process. So as it shrinks because of the gravity, the angular momentum needs to stay the same. The angular momentum for a point particle, if we can treat the star as a point particle, is the mass times velocity times the radius. The mass doesn't change for the most part. So what we're playing with in this case is the radius, the size, and the velocity. If the radius go down, and it does go down drastically, then the only thing that has to keep this the same, because the product of velocity radius stays the same, is that the velocity needs to go up by as much as the radius is shrinking. So the velocity increases, that means it gives me faster and faster rotational speed. And that's basically the essence of that. So it's really the conservation of angular momentum that is the cause of this super fast rotation, okay? With the ever decreasing radius. So again, the jets are really due to the magnetic field. Again, I have an axis of rotation in here. I have north and south pole in here that they're not necessarily aligned. They don't have to. And in this case, for a case of a pulsar, they shouldn't. Okay, for other neutron stars, probably they do. Okay, so for a pulsating star in this case, so the materials in here, they are spiraling. So depending on their charge and depending on the north or south pole, they're going to follow the spiral motion in this case, and that has to do with how a charge in general moves in a magnetic field. And we can show that in the lab, that basically a charged particle that has a velocity, this is called the Lorentz force, by the way, is going to move in a circular motion. But because it has a component in the other direction, the direction with the magnetic field, so it's going to move one way or the other depending on its the charge, the sign of charge, if it's positive or negative, and also if it's the polarity of the magnetic field, if it's north pole or south pole. So the point being in here is that there is a huge jet of particles in here that are charged particles, and a charged particle, when it's accelerated, will always emit radiation. So there is tremendous signal in here that is coming from both sides of the pole of that star. Okay, so you're saying, what are the charges? They're usually two. In this case, for the most part, they're electrons negatively charged and protons positively charged. Okay. So again, this is the continuation of the explanation. As a star basically loses energy in this process because it has that energy of the jets on both sides is going to carry some of the energy of the system. So in this case, ultimately the star starts to slow down. I mean, it starts to slow down because it's losing that energy in the form of emissions on both sides. Sometimes there are spikes in that. There is a gain of speed, and that's because the star actually shrinks a little bit. Actually, neutron stars, they go through neutron quakes, okay, and they're fraction of a second, they crack a little bit. They produce tremendous emissions. But remember, as the size shrinks a little, so the rotation is going to go up again. So MVR is constant. Okay, so if R go down, V go up a little, and then they continue to decrease, losing energy over time. In terms of structure, again, these are based on models at this point. The crust in this case, which is only a few meters, the whole thing is a very tiny object. So imagine the size of the sun. You shrink it all the way to the city of Redlands. Okay? It's extremely small, okay? So it's extremely much smaller than a planet. So unlike, for example, the white dwarfs, which we said that they shrink, but they don't shrink to this size. This is a ridiculously smaller size than what a white dwarf is. So again, this is about 10 kilometers, okay? The size of about 6 miles, basically. Few meters is the crust. For smaller neutron stars, maybe there are remnants of some basically protons, but the main structure in this case are neutrons. Okay? In neutrons, they are packed so close to one another that they start to form some sort of a kind of a chains. Okay, that they're kind of bound together. They're not really. They don't want to be there because of the Pauli exclusion principle, but they are forced by the force of gravity. They cannot go anywhere more than that. Now, what's going on inside the core of a neutron star is something that is a mystery at this point, okay? It could be still a lot of neutrons, at least in the upper layers, but as you go more and more closer to the core of a neutron star, the pressure and the temperature are so high that at this point, even the neutron starts to fall apart, okay? That probably there is a soup of quark matter. And that is something that is completely strange and outside of the scope of what we know about regular matter. So these are extremely different kind of matter. And what I mean by that, probably we will start initially by the regular quarks, which are the up and down quarks. But then there is a transition even under tremendous temperatures, at least this is according to the models of what we think is going on. There's actually transition to the strange quarks, which are a different kind of quarks. So it's not like strange, we don't know what they are. We know what they are, but they are actually strange quarks to the point that this probably, for a little bit more massive neutron stars, it could be actually the entire state of matter for those stars called strange stars. Okay, so again, a lot of these things are based on models, but this is probably what's going on inside a neutron star. Super dense, super basically packed matter that is completely outside of the realm of what we know in terms of regular matter, at least here on Earth and the normal planets anywhere. Okay. Again, stars, or at least pulsar, is probably another stage only of what a neutron star does. Okay, what a neutron star is. So probably older neutron stars, they spin less, so they have less of those because they lost a lot of their energy. Initial stars, there could be actually of tremendous magnetic fields, probably magnetars. Okay, so these are probably different stages. A lot of these things I'm saying probably because of the fact that it's current research and people are working on these fields, trying to have a better understanding of what's going on in here. Okay, again, you have magnetars, pulsars, and also regular neutron stars. They are probably all different versions of the same thing as they evolve in their different stages. Okay, we didn't live long enough. The universe did not exist long enough to see where a neutron star ends or how it ends. Okay. So again, neutron stars can actually form in a binary system. So imagine you have a big star and another big star next to it, and one of them goes supernova and produces a neutron star. During the initial stages, that neutron star has tremendous magnetic field and tremendous also gravity, so it could feed off of that and produce a lot of radiation in the process. This second star also could go supernova and produce a neutron star, and now you have a binary. And this they exist. We saw them. Actually, as a matter of fact, the LIGO detected the collision of two neutron stars. So over time, okay, their gravity starts to pull on one another, and the distance starts to shrink further and further. And as they do, they compress the space between them, the space-time between them, actually, because time now becomes a factor because of tremendous gravities that are involved. So at that point, that produces a collision, and that collision could end up either a neutron star if the two neutron stars were not too big, and also, or probably a black hole or something that is completely different from what we have right now. But we have actual evidence of this phenomenon happening. This collision, this produced tremendous amount of other materials that are past, in this case, atomic mass, atomic number 44. So super heavy materials on the periodic table. Thank you.